meters per second squared. 5 meters per second squared for 5 seconds. We accelerate for 5 seconds. So the final velocity would be 25 meters per second. Well, meters per second. That seconds cancel out one of those. So this would be how we would do a force problem. We use the force to calculate the acceleration. Once we know the acceleration, we can then solve for what the velocity is after a certain length of time. If we know what the initial velocity is, we can calculate what the final velocity is after a certain length of time. So this gives you an example of how we would do these kinds of force problems. So we're really, you can see how this is a continuation of chapters 1, 2, 3, 4, and then now we're adding the force concept. We're still going to use these equations that we used in chapter 4, but now we can actually calculate what the acceleration would be given a certain force. Okay. One of the things we commonly deal with is weight. And weight is a force, but it's a force acting from gravity. So, if we have a certain mass, we know that the acceleration of gravity always acts down. That's why things fall. Whoops. The acceleration of gravity acts down, as we know, and is 9.8 meters per second squared, or in English units, 32 feet per second squared. So we can suppose we have a mass and it's not held and gravity pulls it down. So the force of gravity is the mass times the acceleration, F equal ma. The acceleration is g, that is the acceleration of the acceleration on the Earth, pretty much on the surface of the Earth. So the force of gravity is what we call weight. So the weight is the mass times the acceleration of gravity. And so this weight is a constant force that acts on everything. Okay? So basically, I'm going to now draw it just a little bit differently. Is this, that the weight of this object, which is really the force of gravity on the object, the force of gravity on this object is equal to its mass times the gravitational acceleration. And how fast will it accelerate? Well, it accelerates, that is the acceleration. If it's in free fall, the acceleration is 9.8 meters per second squared. Now, what happens if we have a ceiling, here's say a ceiling, and we have a mass here, but the mass is tied to a rope. Okay? The mass still has a weight acting down on it. That weight is the force of gravity, which is mass times gravity. Now, that's the weight acting down, but it's held up by the rope. So, is its actual acceleration in it? No, the actual the mass isn't moving. It's not accelerating any. If the mass is not accelerating any, what does that tell us? That tells us that that there must be a force pulling back up, and that force is supplied through the tension in the rope. We'll talk more about this actually in next chapter, yes. But I just want to go over this. I'm going to call this F of the force of the rope. So in this case, the sum of the forces are, we have the force of the rope, which acts up, and the weight, which acts down. These two are equal. We know they're equal because the acceleration, they're equal and opposite. The sum of these equals 0. We know that because it doesn't accelerate any. So that means that the force or the tension in the rope is equal to the weight. It's a negative, it's acting in the opposite direction. The negative means that it's acting in the opposite direction. Weight acts down, force of the rope acts up. So the mass does not accelerate any. Okay. Let's see. Let's move on. Okay, now I'm going to move on to page 152 and page 153, where we're going to talk about friction and normal force. Okay, and the friction force, let's see, the friction force really goes on for a couple of pages, but it really kind of gets into it on page 160. And 160 on to page 165, really to the rest of the rest of the chapter is really talking about forces of friction. Okay, when you're dealing with friction, let's draw a picture of this. If we have a mass here, now I'm going to draw the surface as a jagged, rough edge. At some, if you have a purely smooth surface, or what you think to be a smooth surface, if you look at it under magnifying glass or even a microscope, you would see that surface at some scale would start looking jagged. Now, suppose we have another mass on top of that, and that has some kind of jagged surface to it. And then we put these two surfaces in contact with each other, like this. Notice that at some microscopic scale, these two surfaces are actually going to, it's at some microscopic scale, doesn't look so smooth anymore, and we have points of contact, and these points of contact may grab each other, and that's what's causing friction. So, and if you say, well, but even maybe at that micro scale, we're going to smooth it out. Well, you get down to the scale of molecules and individual atoms. At some point, you're going to get jagged points. So, when when these jagged surfaces touch each other, they're going to cling to each other, and you're going to have a certain force to overcome this grabbing of each other. That's the force of friction. So if you push this object, say you push this object to the right, that grabbing, as the object is pushed to the right, the grabbing will tend to resist that motion. So we say there's a friction force back, the force of friction. The force of friction. And the force of friction always acts opposite to the velocity of the mass. That is, here is the surface at rest. If the velocity of the object is going this way, friction always acts opposite. And it has to always act opposite. Suppose the mass were traveling in this way. This way, again, the force of friction would be opposite. The force of friction is always opposes the direction that the mass moves. And this will always be because the surface is always grabbing the bottom surface of the mass, and it always grabs it in a way that resists the motion. So what we say is that the force, if we push the mass to the right, that the friction force acts opposite. Force of friction. Now, what is the size of this friction force? Well, it depends on the surface. So, physicists long time ago determined this, that the weight of this object has a lot to do with this friction. If this object's weight acting down, remember the weight is equal to m times g, the mass times g, this is mass m. If this weight is really, really light, the friction force is less. If the weight is very heavy, then these surfaces are smushed harder together and the friction force is greater. So what physicists have defined is what we call a normal force. This is the force, if the weight acts down, what we call the normal force is the surface, the force of the surface acting up on the mass. Now, what I'm going to do here is we're going to look at Newton's second law. We're going to look at it in the y direction. Remember how in chapter 4 we would look at, when we had two-dimensional motion, we would break that two-dimensional motion into an x component and a y component. We can do the same thing with force. In fact, we will do the same thing with force. It will be much more important in the next chapter, so it will be good for you to get used to it now. When you apply Newton's laws, you apply them in each dimension. So in the y dimension, notice we have the sum of the forces equals mass times acceleration. Now, is this weight moving up or down? No, it's only moving horizontally. So we know that the vertical acceleration is 0. There may be horizontal acceleration, but there is no vertical acceleration. So what does that mean? If the vertical acceleration is 0, the sum of the forces acting on the object in vertical dimension must be 0. Well, we know that. What are the sum of the forces? We have the weight acting down. The weight always acts on the object down. So there's another force that is called the normal force. Normal. That must be equal and opposite. So what we find is that the normal force, what's called the normal force, is minus the acts in the opposite direction as a weight. The weight acts down, the normal force must act up. Okay? How do we interpret the normal force? The normal force would be, remember of the situation of the wall, if this is a table, let's say this is a table, it's basically, it's the table pushing back on, or the table pushing back on the weight of the mass. It's the normal force is what keeps the mass on the table. If you can think of it that way. Think of it also from the point of view, if we have a table, a table has a certain strength capacity, shall we say. If you load up a table really heavy with a lot of mass, what's going to happen? The table is going to break. When the table breaks, the normal force that's able to resist the weight can't resist it anymore, and the whole table accelerates down. Okay? So, in this situation, let's say the table is strong enough to withstand this mass. That means that the normal force is equal and opposite to the weight of the mass. Now, why do we call it normal? What do we mean by normal? Is it as normal as opposed to abnormal? No, no. Physicists have long ago used the word normal to mean perpendicular. So, for instance, suppose I will give you an example. Right now, if we have, well, in this example, we have a table. Whatever the surface is, the normal, what's called the normal, is always perpendicular, is a right angle, perpendicular to that surface. In fact, we could call it force perpendicular, or the perpendicular force, but it's been for a long time, it's been called the normal force. So that's what we call it. Suppose, for example, the table, and in this chapter, chapter 5, we're only dealing with flat surfaces. In the next chapter, we're going to deal with tilted surfaces. So, suppose we put the table on edge, like this. Okay, now we have a mass here. Suppose we have a mass here, and the mass starts to slide. Okay, that's a more complicated situation. We will study that in chapter 6. But for right now, what I want to show you is that whatever the surface is, the normal is always perpendicular to that. So, if you had a weight, if you had a mass sitting here in a table, the normal force would be a force that acts perpendicular to the surface at that angle. It's not vertical anymore. It's tilted because it's normal to the surface. So the normal force is always defined as a force acting perpendicular to whatever surface you're on. So we still haven't gotten a long-winded explanation here, but we still haven't gotten to friction. Okay. But what we do know is that in this particular case, a normal force is equal to the weight. The weight acts down, normal force acts up. Well, this has a lot to do with friction, because friction is defined. Remember, if we push the object this way and the object accelerates, there is a friction force. I'll draw it this way. The friction force that acts opposite. And that the size of the friction force is equal to what's called the coefficient of friction, given the Greek symbol mu, times the normal force. So we first, in order to calculate what the size of the friction force, we first have to calculate the size of the normal force. Then we multiply it by what's called the coefficient of friction. It's basically a constant, coefficient of friction. And this is something we don't theorize about, we just measure it for each particular mass and surface. Obviously, if we have a real rough surface, this coefficient of friction becomes larger. If we have a real smooth surface, this coefficient of friction becomes quite small. In fact, notice that if this number gets exactly equal to 0, there is no more coefficient of friction, then the friction force is 0. That would be a situation where you have a frictionless surface. So a frictionless surface is defined where the coefficient of friction is equal to 0. Notice, in this case, the normal force may be very, very, very large. It doesn't really matter because it's multiplied by this coefficient of friction, which is 0, giving you a friction of 0. Okay? Now there are two types of coefficient of friction. There's what's called a static coefficient of friction, and we give this a symbol mu sub s for static. And then we have the kinetic coefficient of friction, given the symbol mu k for kinetic. What's the difference between these two? The difference is that when an object is not moving, the coefficient of friction we use is the static one. It's not moving. It's in a static condition. It has a certain friction coefficient. Once the object gets moving, though, the friction oftentimes gets less, and we switch from the static coefficient to the kinetic coefficient. As an example, suppose here I have a 2x4 and another 2x4, just to demonstrate. Okay. When I first start pushing this object, it's not really that much. See, I can push it easily. But just for demonstrations, when I first start pushing the object, I have to overcome a larger friction just to get the thing moving. I have to push it a little bit harder, but once I get it pushing, once it gets moving, I don't have to use as much force. Okay. Once the object, if the object is not moving, these little jagged edges at the microscopic level in the surface hold each other, and I have to overcome that initial resistance of the surface. But once and that's given by the static coefficient of friction. Once I overcome that, it becomes easier to push the object. I still have to overcome a little bit of friction, but it's not as much as if the block had stopped. So that's the difference between the static and the kinetic coefficient of friction. In every case, always the static coefficient of friction is greater than the kinetic coefficient of friction. A typical number may be, the static coefficient may be 0.5, the kinetic coefficient of friction may be 0.3. This is just an example. It depends on the surface, obviously. Okay, let's give a typical example of how we might use this. And this would be an example like the one on page 161 to 162 and page 163. And again, I'm just going to make this up. It's not really the one given in the book, but we will make up a typical example. Suppose I have a box on the floor, and the box has a mass of 5 kilograms. And I push against that box with a force that's equal to, let's say, 10 newtons. And I know somehow, I know beforehand that there was a coefficient of static, that the coefficient of static, the coefficient of friction, the static coefficient of friction is 0.4. Okay? What I want to know is well, let me take that back. Let's say I don't know what this force is, but I do know what the coefficient of static friction is, and I want to calculate when will this object start to accelerate. How much force do I have to push in order to just get this box moving? Okay? So basically, the box is stopped, the velocity is 0, and I want the box to just start moving. Okay? How would I solve this problem? I'm going to put up here that the static coefficient of friction is 0.4. Okay. We first look at the sum of the forces. I'm going to write this. Always the first step is look at the sum of the forces in the y dimension. Sum of the forces in the y dimension. We have the weight of the object acting down. The weight is equal to m mass times g. We have the normal force that acts up. Normal force acts up. So we have the weight acting down, and we have the normal force acting up. And the sum of these is 0. We know it's 0 because the acceleration in the y dimension is 0. It's not moving up or down, only horizontal. So this tells us that the normal force is equal to the minus of the weight, which is mg. Okay, mg. Now, for the purposes of calculation, what I'm going to say is that we know that the sign, we know that the direction of the normal force is up. So all we need is the size, the absolute value, the numerical value of the normal force. So that's mg. And so we can ignore the sign just for right now, because we just need the size of the normal force. Now we look at the sum of forces. So that the sum of forces in the x direction. Notice we always look in these two dimensions. We look in the y dimension, and then the sum of forces in the y dimension, and then the sum of forces in the x dimension. Okay, we're going to push with a force F. We don't know what that is, but that's what we want to solve for. Okay. And we know that the friction force, F of friction, acts opposite that. So we're pushing with force this way. We know that the friction force acts opposite. And the sum of these two forces is equal to mass times acceleration. Acceleration in the x direction. Okay. when will this box start to move? It will just barely start to move when this acceleration just goes slightly over 0. We know that when the acceleration is exactly equal to 0, it doesn't move. But if it's just ever so much greater, a little bit greater than 0, the box starts to move, correct? So what that means is that we have to solve for the condition when the force minus the friction force is just a little bit greater than 0. Or what we can say is that the friction force, the force that we push with, if we say this is essentially 0, the force we push with must be equal to the friction force, and it must just barely exceed, that is, I'm going to put, we have to at least equal the friction force, and this just barely exceeds it. So we have to just be a little bit over the friction force.